probably change slide myself.
Yeah, you will do it on that one.
Okay.
Yep. So, Trydell will tell you about Yurimaco, the mixed material joining project with new joining methods, right?
Yes, exactly. And like Yvonne, I was also told to have an interesting title. And I don't know how well I succeeded either, but the innovative methods for joining of mixed lightweight material combinations. And my name is Klara Trydell, and I work as a researcher at Swerim at the joining department. So you have the scope and objective here. The overall aim for the project was to achieve strategies for joining of structural components, combining ultra-high strength steel to lightweight alloys, for example, die-cast or extruded aluminium. It is a Vinnova FFI project, so sustainable production. And as you can see here, when you look at the project duration, we are finishing up the project. So I actually have a lot of results, and I tried to make a decent selection, but I don't know if I succeeded. So please let me know if I'm running short in time, and I'll try to speed it up. But in the project consortia, we have the OEMs, Volvo Cars and Scania. For component manufacturers for the industry or automotive industry, we have Gestamp. And then for provider of steel material, we have ArcelorMittal. And then on the aluminium side, we have Hydro, which provided, of course, extruded aluminium alloys. And then we have the aluminium casting company, Ages, that work with the recycled aluminium. And then when we look into the joining solutions themselves, the joining solutions we focused on in this project, on the friction element welding side, we have AOT that have developed the AOL technique. And then for resistance element welding, we have RB&W, who have developed a solution or designed a solution for resistance elements. And then, of course, project leaders is Swerim in this case. So just quickly some background. As you're all very aware, electrification within the automotive industry is increasing. And to assure driving range and also to maintain collision safety, we need to incorporate more high-strength steel material, and then also in combination with these lightweight alloys. So in a car, you will of course have meeting points for these two materials, and then you have to have a robust and a suitable joining method. Yes. So just very quickly, because I mentioned that I have a lot of results, I will kind of go through the background a little bit quicker. But there are, of course, already more conventional solutions on the market for joining mixed material combinations. For example, you have self-piercing rivets or flow drill screws. And both these cases, you have a lot of different designs and different solutions, and you can work with clearance holes and etc. to increase the range of in which material applications these two methods can be applied. But very much a generalization, but there is a constraint in the strength of the steel material and the thickness of the combination. So you can approximately around 800 megapascal at the thickness of 1.5 millimeter for the steel material is something that you can keep in mind for these more conventional techniques. So if we go back to the Yurimaco project itself, we kind of divided the project into 4 different stages. And in stage 1, we focused on influence on material properties. How do the material properties change, and how can we ensure sufficient strength of the joint itself? And also, of course, optimization of process parameters. Are these material combinations joinable? And in stage 2, we try to simulate more of production reality by introducing disturbance factors. So, for example, introducing a gap between plates or varying distance to edge to simulate a varying flange distance. Stage 3, joining of components or component-like geometries. Here we scale up the trials in stage 2. So we take the disturber factors that seem to have the largest influence and scale up to a more component-like part to see if anything happens when you scale it up. And then stage 4, joining of demonstrator, of course. And then we come into the actual joining methods that we have mainly focused on in this project. I mentioned resistance element welding, which you can see a cross-section of a typical joint here to the right, and friction element welding, where you can see a typical joint to the left. So if we talk a little bit more about the techniques themselves. So for resistance element welding, we had a resistance element called SPAC plug developed by RB&W. And the element itself is punched into the top material in this case. And as you can see, the surface is quite flat in this design. And then in the bottom picture, you can see the material flipped around, so where it's actually to be joined, where you can see a small projection in the element. So this element is mechanically locked into the aluminium sheet, and then you use your standardized spot welding equipment for joining. So the spot welding itself happens between a steel element to a steel plate. Yes. And then if we take a look at the friction element welding instead, the process developed by AYOT. It is a thermomechanical process to join lightweight material to steel. So in this case, you place your lightweight material on top and then your steel on the bottom. And in this process, you mainly set rotation and friction, and then you progress in the program itself by position of the element. So you predetermine a distance, a predetermined distance, the next step is initiated. And the first step is penetration of aluminium, where you penetrate aluminium with your element by force and rotation, of course. And then step number 2, which is called the cleaning step, is initiated. So as I mentioned, this position, when the position of the element reaches the steel top surface, the rotation is increased. And this helps with cleaning or activating the surface, they call it. So impurities or coating, etc., follows the element and flows up into the, when the element is deformed into the material. And then step number 3 is the welding step itself. And at this step, a friction weld is created. So it's not, you do not mix the material. They're not traditional melted joints as such. It's a friction weld. And then at the very last step, you stop the rotation and you increase the force. And this is a compression step to help lock everything in place. And here you can see 2 different elements. You have the bigger CFF element and the smaller SRE element. And they work basically the same. So some advantages and disadvantages. Of course, both these methods can be applied to brittle ultra-high strength steel. That's the reason we have them in the project. If we look at friction element welding, this does not require a pre-punched hole, no surface preparation, and you get a relatively small heat effective zone. It does require 2-sided access, and you do also need a specialized equipment. For resistance element welding, a large positive aspect is, of course, that you can use your standardized spot welding equipment that is already in place in many manufacturing plants. You can also apply your knowledge and experience from spot welding onto this process. It is a fast method once the cover sheet is prepared with the resistance element. Also in this case, you need 2-sided access, of course, the punching operation, and then you can get some potential stress concentration from the hole generation. Then just very, very briefly, stage 1 from the project. I mentioned we focused on the material properties. So in this case, we of course had quite a large matrix containing a lot of different steels, a lot of different thicknesses, and then also some lightweight material. So both cast aluminium without heat treatment and a cast aluminium with heat treatment, extruded aluminium and sheet aluminium. And to our help here, we had 2 master thesis students. So if you want to look up the resistance element side of this, you can search for Malte Eriksson, student at KTH. And for friction element welding, we had help from Hilda Westberg from Luleå Tekniska Högskola. So just briefly how we worked with these methods. First, for resistance element welding, we of course optimized the process for the material combination. Generation of 1D lobes, which is basically at the predetermined minimum nugget size, the number of current steps you can achieve before a spatter or expulsion occurs in the joining. So you get the current interval called the approved current interval. They were evaluated by cross-section analysis, which basically means that we measured the nugget size. And then, of course, shear tensile and cross-tension testing. For friction element welding, we used the iterative process to get the best possible parameters in the first step, the penetration of aluminium step, to assure that we get a smooth halo around the joint and a good mechanical interlocking without ship formation. Then we used, you can see, the internal and external quality criteria that we made sure were obtained with the parameters. And then, of course, shear tensile testing and cross-tension testing. And just to mention very, very briefly here, here you can see a 1D lobe to the right from the resistance element welding. So here you can see the approved current interval and the cross section. Just when comparing joining cast aluminium or extruded aluminium, we saw for resistance element welding the same approved current range. With friction element welding, we saw that when we used cast aluminium alloy without heat treatment, it was very brittle, and therefore you tended to get more ship formation around the head of the element. And the ship formation could work as an initial point for galvanic corrosion, for example. But here in the image, you actually see the other cast aluminium alloy, where we don't see the same problems because of the increased ductility. Yes, and then I move on to the robustness of the process. So here we had quite a lot of different factors, and I'm not sure I will be able to go through them all, but we tried varying distance to edge, for example. And the main thing to take with us from here is that the inner diameter of the pressure module for friction element welding determines how close to the flange you can be. So when you have very narrow flanges in, for example, door frames, it is common to use this smaller SRE element. When looking at the shear tensile testing curves, we can kind of see a drop in shear tensile strength, but this is probably more due to the fact that we have less aluminium to actually take up the force when we pull the specimens apart, since the element is placed closer to the edge. In resistance element welding, we have the minimum approved current from the 1D lobe generation, medium and maximum current. And we don't see much of an influence, maybe a tendency towards decreased nugget size for the high current when moving closer to the edge. During this experiment, we also saw that there could be an increased tendency towards expulsion for the different current intervals. So I think that's that there. And then maybe the most important thing, varying aluminium thickness, which is of course very important when we have these cast components, because they tend to vary a lot in thickness. And here we tested joining with the same parameters from the reference being 3 millimeter aluminium. And here we instead tried to join 2.6 millimeter and 3.4 millimeter. So for friction element welding, you can see that when you decrease the thickness, you get more of an underhead filling, which is not desired. And instead, when you increase the thickness, you can see maybe that the friction weld tends to become a bit smaller. And in this case, you should modify the process a bit depending on the thickness variation in your cast component. So, for example, the element length itself should be determined by the thickest part in the aluminium component. For resistance element welding, we actually did not see any influence on the nugget size testing with different aluminium thickness and at different current. It is also worth mentioning that in this case we used constant current, and there could be possible benefits using adaptive welding system. Adhesive, we saw that it was possible to join with adhesive. That was not a big problem really. In friction element welding, the adhesive is pushed away from the joining area, and in resistance element welding, we saw bigger differences when the joints were welded on different sites than actually we saw with different adhesive or different adhesive thickness. It is also possible that this little projection in the resistance element could help with contact. So this projection could maybe even facilitate a bit when including an adhesive in the joint, if compared to traditional spot welding. We tested gap between sheets, not a problem for friction element welding. We still haven't tested resistance element welding. This we scaled up to the bigger hat profiles, and we saw that we got full pull-out plug failure when we pill tested. We tested angle fault or misalignment of welding electrodes, and we did not really see any impact here on the process robustness. But then, of course, for resistance element welding, there is always the problem that you do not hit your resistance element in the center itself. You might miss it somewhat. So we tried missing 2.5 millimeters or 5 millimeters. And here we do see a clear impact both in shear tensile strength and in weld nugget size. So to summarize, general process time, 0.5 to 1 second for resistance element welding. I forgot to mention this, but of course, when we do actually place the elements closer to the edge of the material, you do see deformation and you see bulging. We also tested varying steel hardening parameters, so not optimal hardening condition. This did not impact the process at all. So from the resistance element welding, what we can say is that the misalignment of the electrodes are the main issue when it comes to this method. For friction element welding, overall the joint quality was not significantly affected. In those cases that we did see some sort of effect, there are often adjustments you can make in the process itself if they are known to you, that can help you overcome these issues. So in Yodimaco, we will continue stage 2 and include some casted coupons from this snake tool, which has been designed to be very good in the start of the casting process, and then as you move towards the end, there is accumulation of impurities and thickness variations and so on. As I mentioned, we will continue with the component scale or testing with the hat profiles, introducing the different disturbance factors, and then stage 4 demonstrator. So conclusions this far, it seems that both the resistance element welding and the friction element welding are suitable methods. Of course, parameter optimization is needed, but it seems like you can get a relatively robust joining process. Future work. This project has come very, very far. So future work would include how to incorporate this into an actual production line. Of course, also inline quality assurance, and then also look into the possibilities with adaptive systems for resistance element welding. And based on the discussion, I guess another point should be disassembly and how to recycle and work with that. So I think that was all I had. And of course, you will be able to get the presentation afterwards, so you can look a bit more into the results if you would like to.
Thank you, Klara. Any
Thank you.
questions to Klara?
What was the surface treatment of the ingoing metals, aluminum and steel?
Surface treatment, the cast material was as cast, and then I don't think they had any surface treatment, any of the materials. Do you remember, David?
No, I don't remember.
No, no, I think they did not have any surface treatment. Oh, the steels, they are coated aluminium silica.
Okay.
Yeah.
Okay.
Yeah,
Typically 35 microns. Commonly.
Yeah.
More?
Maybe just an amateur question. In adhesive joints, one of the known effects is the fatigue, aging and fatigue. You're showing a replacement, two alternative processes to adhesive. Have you tested for fatigue strength?
We have not tested for fatigue strength. No.
But it will behave like a spot weld, similarly, because it is a spot formed joint. And such a joint bears load in the outer perimeter. So depending on the diameter of the spot, you can calculate the stress concentration around that. Somewhere between 10 and 15 is the common KX for that situation. But it can also be used in combination with adhesives. So it's not necessarily replacing. It can be combined. Often in automotive, you would like both adhesives and a spot joining method. So you would like to have both.
Yeah, and
to have tightness and flutter.
Of course. And then also in this case where you join aluminium to steel, you would of course like to incorporate an adhesive to get rid of the corrosion problems.
You know?
In conclusion, is one better than the other as well as this few and few? And then how do they compare to the ones that you showed right at the start? Where
compared to the ones right at the start, I guess the benefit is that you're actually able to increase the strength of your steel material. So if we remember the thickness 1.5, 800 megapascal around. In this project, we have mainly focused on joining UC bore 1500 and up to 2000. So that would of course be the benefit when it comes to that. And comparing the two methods, it is extremely hard because the resistance element welding, you do have the very positive aspect that you can use your already in place equipment, and that is a huge benefit. In terms of the methods, they of course they have the positive and negative aspects both to them. For resistance element welding, as shown, is very important that you actually hit the element in the center, which is not the problem you have with friction element, for example.
is that an issue in an automotive?
I think it could be an issue if it's something you have to work.
Slightly more robust then.
Yeah, if you, I guess if you are aware of the problem, you could always find ways to work around it.
Maybe it shouldn't be a problem.
No.
However, things may happen. Yeah. More comments, questions? No, then I think we should thank Klara.
Oh.
It remains for us.
Yeah.
To,
Close the session.
close the session and say thank you very much for coming. Now it will be coffee waiting before
Yes.
we all gather into the black box again, I guess.
Yeah, 15:30 in the black box again, and now coffee in the foyer. Yes, thank you very much.
Thank you very much.
Det är ju vad som heter en tag i. Det finns ju en ingrediens. Och där finns ju men jag är i det blir ju en grupp som jobbar. Men sammanläggande så är det